the electric potential. So the electric potential or voltage at a particular point in space. So you can see here that the argument to the potential is a position vector. And it asks, what is the electric potential that I experience at this point in the space due to all surrounding charge in space? So the prime, so notice the element of integration is a volume, an element volume, but it's prime because it's looking at all other points in space not equal to the actual point where you're located at, where you're looking around you and asking the question, what field potential am I experiencing because of all the surrounding charge? So you can note in relation to this integral in particular that we're excluding the position r equals r primed when we're doing this integral. Rho, remember, was the volume charge density, that is the charge per unit volume. What we did was to look at, I should have here, we're looking at we had this application of nabla. So in your notes now, if you put nabla, which is a spatial integral as you know in 3D, it operates on particularly the denominator in the integrand. I gave you an exercise to go away, but you actually should have given you here that it's just taking the modulus of the position vector r. So if you apply nabla to the modulus of the position vector r in the denominator here, what you should do is, what you should get is arriving at this expression here. So effectively, nabla on 1 on r is a shorthand for writing either this expression, which also equals 1 on r squared multiplied by a unit vector r. Because this 1 on r squared law is what you always see in electrostatics and also in the gravitational field theory. And notice that here, by definition, modulus is the square root of the Pythagorean component that you always get. So if you want to know the distance you are from the origin to the point in space, you apply Pythagoras' theorem in its general sense. X squared plus y squared, but now z squared, which is in three-dimensional space, and then the square root of all of that. So if you recognize that this is the same as, and you apply nabla to that expression, then you should arrive at this original expression that we had from Coulomb's law. Okay? So that's what we got to this time last week. So the task now we have to find dV So for the first half of this lecture, what we're going to look at is how to find the divergence of the electric field and the curl of the electric field for the electrostatic case. Because remember, the dV and curly together are required to define absolutely uniquely what the electric field is going to be. Now we noted that so we can first of all note that now the electric field is the negative gradient of voltage. And what I've done here is to, if you want to be pedantic about the notation, what you could do here is to put in that we're looking at a particular point in space and it roams over all space. Or you can just simply put electric field equals the negative gradient of the potential. Now we know that the potential is a scalar field function. And the gradient of a scalar field function generates a vector field, but a vector field that has a very special property, that is conservative. So we get for free, automatically, that curl cross equals 0. We've already established that, so we get that for free simply because of the way the electric field has come to be established. So that implies that the electric field, that implies that the curl of E equals 0. So we've arrived very quickly at our first result. We found curl E. What remains now is to find the divergence of E. And to find div E, what we can do is to find divergence of E, you can apply Gauss's or the divergence theorem. So Gauss's divergence theorem, remember, was an integral transform. It enabled you to go from a volume integral to a surface integral. So the volume integral, if you recall, looked at three-dimensional space, and we looked at the argument, or the integrand of the integral, was the divergence. And in this case we had the general field A, but now we can talk about a particular field, which is the electric field in this case. So there's our element of integration, the volume element. There's the integrand to the volume integral, so that's the volume part of Gauss's divergence theorem. And it has to be related to a surface integral. And we can talk about the elements of integration for the surface being d sigma. It has, remember that an area is a vector. An area always faces in a certain direction. So here we split off the magnitude of the vector from the direction of wherever it's pointing. So we talk about the unit vector of the element area. And we take the inner product, the dot product, with respect to the electric field. So there's Gauss's theorem, Gauss's divergence theorem. We now need to apply that in order to find out what div E actually turns out to be equal to. So we can expand that and note that we've got our area and our element of integration still. But if you go back to Coulomb's law, you notice that the electric field can be defined in terms of charge and space. So the electric field is going to be equal to, we've got a cos theta relation, so there's, because remember that the dot product, the vector inner product, is going to be equal to cos theta. We've actually looked at the magnitudes of each of these separate quantities. So cos theta, and the electric field, remember, was defined in terms of charge, Q, over R squared. So all this part here is the magnitude of the electric field. Now as it happens, if any of you have done spherical trigonometry, you'll recognize that by definition you can define a solid angle as equal to cos theta over R squared. So that if you integrate over all space, so if you imagine here a we use our coordinate system Z, X, Y, and we've got a sphere of some radius about the origin, we can talk about a certain cone. I'll just stick the origin this side. So imagine here you've got a cone of a certain angle, and it has a little solid angle, delta omega, a bit like an ice cream cone. It looks out, and rather than being a plane angle, you revolve that plane angle and generate a solid angle. And that solid angle can operate over all possible directions of pointing. And I talk about 4 pi steradians being the definition for full space. So if you integrate from 0 steradians to 4 pi steradians, so this superscript C is the definition for a steradian angle. It's equivalent to so if you have a plane angle and you've got the degree sign, you've got theta degrees. It's a plane angle, degree angle. In solid angles, you have a steradian angle, and that's the same idea that's applied there. So now you're looking at the integral of that element angle sweeping around the xy plane and in the yz plane. It will equal 4 pi. So the result of the integral is that you have a volume integral of, there's our element of integration. The integrand is the divergence of electric field, and just putting the rest of turns out to be 4 pi cubed, where the 4 pi has come from the definition that we have here for an element solid angle, delta omega equals cos theta over r squared. Now if you've never done spherical trigonometry, you can still arrive at this 4 pi relation using an extension of planar trigonometry. So if again you construct your coordinate system, so you talk about here as a mathematical detour. So these are just some side notes that you can stick in the main flow of your notes. This is an alternative way of arriving at this 4 pi result when we take this, when we perform this integral. This is a surface integral. So what we're doing is, if we go back to our original consideration where you've got, for example, draw a larger sphere. Remember this can be a soap bubble, and a soap bubble can be a very irregular volume which has a very irregular closed surface. But you could mathematically, ideally, deform it to adopt a very regular shape, like a sphere, for example. And recall that who knows what the electrostatic field's doing? It could be fluxing through space in some arbitrary manner, and you've got an element of the surface, and it's looking out in some particular direction. So there's our element surface area, and it has a direction of facing like that. The electric field might be going off in this direction, so that when we do the dot product, we're actually wanting to know, because we know from, we look at the definition of the cosine integral, or cosine rather, so pi on 2, pi, 3 pi on 2, it's bounded between 1 and minus 1. It will do this so that A dot B, AB cos theta, theta takes on its maximum ordinate value when the argument is going to be 0 degrees. So if A is parallel to B, you have the most component of one vector aligned with the other vector. So in this case here, the action or the operation of this integral is to project, is to ask the question, how much of this electric field is actually lying in the direction that the element area is facing. So the electric field here, at this point, you project the electric field onto the unit vector of the surface, normal. And then you've found out how much of the field is lying in the direction that the element's facing. And then you're integrating over the total surface, asking how much the field is lying parallel. What component of the field is lying parallel to that surface element? So, pictorially, that's what's going on when we're doing this particular integral. So, if, for example, we had our charge at the origin here, and we've got our surface, and you can imagine that it occupies, if you revolve that about any of these axes to generate a sphere, then, for example, you take a radius out to where it touches the sphere, and we can locate where this radius is in a number of orthogonal coordinate systems. We can use the x and the y and the z address, but because we're working in spherical coordinates and plane spherical coordinates, since we're integrating with respect to an angle theta, they define a polar angle. If you take an angle down from the z-axis, they define that as the polar angle, and it's always measured in theta. So originally the radius vector started here, and you come down and you stop at a certain angle theta. So along the z-axis, we have theta equals 0 degrees. You can project, that is, if you had a torch and you shone your torch down the z-axis onto the xy plane, that radius vector would cast a shadow onto the xy plane. And so you'd have the shadow doing something, so you could project that vector down onto the xy plane, and there's its shadow on the xy plane. And it has a particular length. It's going to be r sine theta. If we were to swing that shadow in the xy plane by a certain small angle, so let's say we moved it by a small amount, like that, for example. So in here, we have a little delta phi. In the literature, phi is always reserved for sweeping an angle out in the xy plane. They call this the azimuth angle. So for those of you who are doing antenna projects, they talk about, in antenna theory, a polar angle and an azimuth angle. Well, this is what they're talking about. The polar angle is the way you rotate your antenna in space with respect to the z-axis. And the z-axis is normally reserved for the direction of beam propagation or power propagation. And the azimuth plane is orthogonal to that. And you sweep out, as you sweep that angle out, you also sweep out an arc segment. And this is going to have a length that's going to be proportional to the angle. So it's going to be the radius, which is r sine theta phi. So that's just a little swing in the azimuth angle. We can also take a little swing in the theta angle. So we could have also swung this vector this way, so there's a delta theta, and likewise you can have a little arc, and it's going to be r d theta. So combining these two, because if you swing in both theta and phi, what you end up doing is generating a surface area. Actually, I'll just move this r d theta out of it. So here's our delta sigma. This is our element area, and it will have a certain facing outwards into space somewhere. So delta sigma here is going to be, so if you take our projection back to there, that projects, so you can be a better artist than I am. So you can see here we've got, in this sense, from here to here is our r sine theta d phi, and here's our r d theta. So now we just multiply this edge by this edge, as you would normally do to get the equation for an area, so that delta sigma is r squared sine theta d theta d phi. So now you just plug this expression back into what we have in the equation from Gauss's theorem. And what you can do is, so what do we have here? We've got an integral over a surface, and now we've got, I'll just split off the two elements of integration. We've got d phi, I'll get rid of the s here. Now, that can go from theta equals 0 degrees, where it's pointing right up the z-axis, and we'll swing it all the way down until, well actually we can go through a full revolution, in fact, so we can talk about a 2 pi swing, so that it does a complete revolution back to theta equals 0 degrees. And then we can look at the, then the phi, we can split off into two parts. We can look at one hemisphere, do the calculation, and then just double the result to get the full volume that we're looking to work with. So we can just look from 0 to 180 degrees. Now, we notice that in this situation here, the electric field part is not under the action of the element of integration, because remember here, delta sigma, if you look at that diagram, is only in d theta and d phi. It's not a function of delta r. So this component here can actually travel outside the operation of the integral and sit outside the integral. So we've got our q and our r squared term sitting outside. We've got, so that should be, so keep that defined, so that's in the plane, and delta theta, and then we've got the r squared sine theta, and then we've got cos theta, now the r squareds can cancel here, so that all you're really doing is performing this particular integral. Now that's a fairly standard integral, because if you go back to your first year notes, they will have taught you integration by substitution as one method. So if you let, for example, an arbitrary u equals sine theta, for example, then du is cos theta d theta, so your integral becomes du u. Remember that you change your limits of integration from phi equals 0 to pi according to your new integral. I'll let you go through this exercise. It's a fairly simple integral, but what you end up doing is getting a 2 pi answer, and that's for one hemisphere, which would be for this side. If you just double the result, then you take the other hemisphere and get the full volume. So when you multiply by the other hemisphere, you get the 4 pi answer, which is the same result as you get if you are able to use your spherical trigonometry. If you're familiar with solid angle geometry, then you can go directly to the result that way. If you're not aware of it or unfamiliar with it, then you can work in the way I've just shown you here and obtain the same result, 4 pi. Because now what we do, remember, is we want to come back to relating volumes. Here so far, what we've done is to work with Go back, where's our Q here, Q. Q, remember, we can turn into a volume charge density. So we can talk about an integral over space of charge density, which if you integrate over the volume, you come to the total charge. So we'll express this charge Q as coming from the integration of a volume. So all that scribble over there on that far right-hand board is really just detour supplementary notes that if you want to go away and think about, so you don't have to put that in your notes. So just do it for those of you who need to go away and convince yourself that what we're going to arrive at is what we term as Gauss's divergence theorem when it applies in electrostatics. So we can talk about a volume integral, and again we're integrating over space. I'm not going to prime it in this particular case, but if we've got a volume charge density, so that's going to be what the total charge happens to be. If you want to put here a subscript tot, it's short for total. So the total charge is just integrating over the volume for the charge density that we happen to have. Going back to Gauss's theorem, we've also got a volume integral that operates over an element of integration, a volume element of integration, and is the divergence of the electric field. And so what we found is it implies, if you look at these two volumes here, the volumes themselves are immaterial. They're arbitrarily connected, but these two volumes can be treated as being identical. So what we do is we pay attention particularly to the integrand. So therefore, the integrand of this volume integral is identical to the integrand of this volume integral. And it implies that the divergence of the electric field is equal to 4 pi rho. The application of Gauss's divergence theorem leads directly to the definition for the divergence of the electric field. Notice that it's non-zero, which means that the divergence operator has done its job and it's found a source of field, charge. So if we go back again to the idea of a bubble, you've got a cluster of charge, etc. Our bubble happens to have wandered into this region of space, and we've got field flux lines, and now we've got a net outflow of flux that's not cancelled by a counterflowing inflow of flux. So our non-zero result is what we've expressed here as 4 pi rho. So now we've totally defined the electric field, the electrostatic field, using Helmholtz theorem. Remember, Helmholtz theorem demanded of us that we had both div and curly in order to define the field properly. So there we have it now. There's div, 4 pi rho, and there's curly, 0. And the zero result enforces that the electrostatic field is conservative. So that if you do work to move charge around in an electrostatic field, you've got conserved action. So I'll just jot down those few points in some notes. And that pretty much summarises what we need to know about electrostatics in terms of the way Helmholtz theorem works. And we can apply now a similar procedure for magnetostatics.